So imagine buying like a large, incredibly expensive pizza, right? But before you can even take a single bite, you are legally required to just throw 3/4 of it directly into the trash.
Right, which sounds completely insane.
It does, but I mean, if you drive a gas-powered car, the actual laws of physics are forcing you to do exactly that every single time you fill up your tank.
Yeah, it sounds absurd when you frame it like that, but mathematically, that is precisely the tax we pay for the sheer convenience of the internal combustion engine.
Welcome to Insight. We've got this massive stack of technical dossiers you sent over regarding the whole EV transition, and well, our mission today is to just cut through all the political noise.
Yeah, there's a lot of it.
So much, because you are constantly bombarded with these conflicting headlines, right? One day EVs are going to save the world, and then the next day you're reading that, gas engines are making this huge comeback.
Exactly. So today, we are completely ignoring the boardroom mandates, the environmental rhetoric, all of it.
Right. We are looking exclusively at the brutal, unforgiving laws of physics and engineering that are actually driving this massive industrial transition.
Yeah, we're pulling from some really dense sources today, covering thermodynamic limits, electrochemical bottlenecks, and heavy infrastructure supply chains. Our goal is to just impartially report what the data and the actual mechanics say.
And we are going to start right at the very heart of the conflict, which is the engine itself. Because, the internal combustion engine has been fine-tuned for over a century.
Right.
Hundreds of billions of dollars have been poured into making it, absolutely perfect. So why are automakers acting like it has just suddenly hit a brick wall?
Well, honestly, because of Sadi Carnot.
Wait, who?
Sadi Carnot. Back in 1824, this French physicist established a mathematical formula for the maximum theoretical efficiency of any heat engine.
Okay, 1824. That's a long time ago.
Yeah, and the Carnot limit essentially dictates that an engine's efficiency is strictly limited by the temperature difference between the really hot combustion chamber inside and the cold ambient air outside.
Meaning the engine has to get incredibly hot to generate power.
Yeah.
But there has to be a physical limit to that heat, right?
Exactly, there is. A gas engine relies on violent exothermic reactions. It is literally a series of controlled explosions.
It generates a ton of heat.
Yeah, so much heat that it would physically melt its own steel and aluminum structural components if it didn't actively reject massive amounts of that heat through, liquid cooling systems, radiators, and exhaust gases.
So shedding all that heat just to save the metal, that is where we lose the pizza.
Precisely. And this isn't a design flaw that legacy automakers can just, put a team of engineers on and fix. It's a fundamental requirement of the second law of thermodynamics.
So it's literally impossible to fix.
Right. Under peak, highly controlled laboratory conditions, legacy auto has actually managed to push internal combustion efficiency to around 50%.
Okay, 50% doesn't sound terrible.
In the lab, sure. But when you look at real-world driving conditions, like accelerating onto a highway, sitting at a red light, fighting wind resistance, the mechanical efficiency drops to merely 20 to 30%.
Wow.
Yeah, so up to 80% of the energy in the gasoline you just paid for is completely lost to heat and friction.
Up to 80%. Okay, so that's the physical ceiling for burning fuel. How does the battery electric vehicle, or, the BEV, actually bypass that Carnot limit? Are electric motors just built better?
Well, they operate in a completely different physical paradigm. BEVs bypass thermodynamic combustion entirely in favor of direct electrochemical energy conversion.
Right, so no micro-explosions.
Exactly. You aren't creating explosions. You are using magnetic fields to spin a rotor. And because there is so little heat waste, modern electric motors convert 85 to 95% of their onboard electrical energy directly into kinetic motion.
Okay, I have to pause you right there because that brings up the long tailpipe theory. I hear this argument all the time.
Oh, sure.
People say, okay, the electric motor is super efficient, but if you charge an EV on a grid that's powered by a coal plant, aren't you basically just moving the smokestack from the car to the power plant and completely negating any environmental benefit?
Yeah, that's a really common talking point. But the dossiers actually systematically dismantle that specific claim by calculating what's called well-to-wheel efficiency.
Okay, walk me through that.
Let's look at the actual mechanics of charging an EV on a dirty grid. So when you transmit power from a plant, you lose about 5% over the power lines.
Right.
Then the power hits your house as alternating current, or AC.
Yeah.
But your car's battery stores direct current, or DC.
Right, so there's a conversion there.
Yeah, and converting that power bleeds off heat. I mean, that's literally why your phone charging cable feels warm.
So you're losing energy at the plug, too.
Yes, the inversion process is about 85.7% efficient. But even when you calculate all of those systemic losses like the grid transmission, the AC to DC conversion, and the motor itself, BEVs, still yield a total well-to-wheel efficiency of 59 to 77%.
Wait, compared to the 20 to 30% of the gas car?
Exactly. The difference is staggering. I mean, centralized power plants, even the ones burning coal or natural gas, operate at much, much higher thermal efficiencies than millions of tiny distributed combustion engines stuck in traffic.
Oh, that makes total sense.
Yeah, the sources show that even on heavily coal-dependent electrical grids, EVs produce up to 40% less greenhouse gas emissions over their lifetime compared to equivalent gas cars.
Wow, 40% even on coal.
Right. And when you factor in manufacturing and battery disposal, overall life cycle emissions are 73% lower. I mean, a technology that is mathematically 3 to 4 times more efficient at converting energy into motion is inevitably going to win out on an industrial scale.
Which brings us to this massive paradox. If the electric motor is this, mathematically superior marvel of efficiency, why is my gas tank still so incredibly convenient? Why aren't EVs absolutely everywhere by now?
Because while the electric motor is virtually perfect, the battery powering it is severely flawed when compared to the chemical miracle that is gasoline.
Okay, this is the energy density problem.
Yeah.
We traded a heat problem for a weight problem.
Exactly. Gasoline is, from an engineering standpoint, a nearly perfect energy storage medium. It has a staggering gravimetric energy density of roughly 12,000 watt-hours per kilogram.
Okay, that sounds like a lot.
It is. But here's the really crucial part. An internal combustion vehicle does not have to carry its own oxidizer.
Right, it just breathes the ambient air as it drives.
Exactly. It breathes the air, burns the fuel, and continuously sheds mass out of the tailpipe. I mean, a gas car physically gets lighter the further you drive it.
Oh, right.
But a battery, on the other hand, is a closed system. It has to carry absolutely everything it needs for the chemical reaction.
It's like dragging heavy luggage everywhere you go. What exactly is weighing it down so much?
Well, the lithium that actually stores the energy is only a tiny fraction of the total weight. The battery pack is burdened by the cathode, the anode, the liquid electrolytes, the heavy thermal cooling systems, and the heavy steel safety casings.
Just a ton of dead weight.
Yeah. Today, the industry relies on 2 main chemistries. There's NMC nickel manganese cobalt. It has higher energy density, but uses incredibly expensive, sometimes volatile metals.
Right.
And then there's LFP, or lithium iron phosphate, which is cheaper and highly durable, but holds even less energy.
So how does the very best NMC battery compare to, a tank of gasoline?
Even the absolute bleeding-edge NMC battery holds 40 to 50 times less energy per kilogram than a tank of gas.
Wait, 40 to 50 times less. Not percent, but times. That isn't just a slight disadvantage. That is an absolute canyon.
It is. It creates what engineers call a severe mass penalty. To give consumers that highly demanded 300 to 400-mile driving range, automakers literally have to pack the car with thousands of battery cells.
Right.
As a result, EVs routinely weigh 20 to 30% more than an equivalent gas car. I mean, we are seeing large electric pickup trucks hitting the market that weigh over 7,000 pounds.
Oh my gosh.
Yeah, with the battery pack alone weighing close to 3,000 pounds.
Okay, I have a major question here because the mass penalty has sparked a massive controversy.
Oh, I know where this is going.
Yeah, if these vehicles are so much heavier, aren't they just shredding their tires on the asphalt? I saw this huge headline claiming that EV tire wear microplastics are 1,000 times worse than exhaust fumes, and that we're basically just treating tailpipe smog for toxic rubber in our water supply.
Yes, this is one of the most polarized debates in the whole transition. And we really need to look at what the rigorous academic data says versus, the sensationalized headlines.
So what's the real story?
Well, independent testing firms did publish claims that tire wear could be up to 1,000 times worse, calculating up to 5.8 grams of particulate matter per kilometer.
Okay, that sounds really high.
And the core concern is totally valid. Tires shed microplastics, including a chemical called 6-PDD-quinone, which prevents the rubber from degrading, but is highly toxic to marine life when it washes into storm drains.
But are EVs actually shedding 1,000 times more of it?
No. The most recent comprehensive data from the Virginia Tech Transportation Institute and the UK's Ricardo Phase 2 study from late 2025 provides a really critical correction to those numbers.
Okay, what did they find?
Yes, heavier EVs exert far more shear stress on tires during acceleration. That's true. But They aggressively offset this through a mechanism called regenerative braking.
Right, that's when the electric motor runs in reverse to slow the car down, and it captures the energy to put back in the battery.
Exactly. Because EVs use the magnetic resistance of the motor to slow down rather than, clamping physical brake pads onto a metal rotor, they actually reduce friction brake dust by over 80%.
Oh, wow. So you're losing tire material but saving on brake dust.
Precisely. When researchers measured the total non-exhaust emissions factoring in both the increased tire shear and the drastically reduced brake dust, actual particulate emissions sit closer to 1.1 to 2.7 milligrams per kilometer.
Oh, okay. That is vastly lower than those 5.8 gram figures.
Extremely lower.
So we definitively eliminate the toxic tailpipe pollutants like nitrogen oxides, and we basically eliminate brake dust. But that stubborn mass penalty means localized particulate pollution from heavier tires is still a real physical friction point.
Yeah, it remains a very real problem. It's going to require advanced tire chemistry and strict policies to fully resolve.
Which naturally forces us into the next bottleneck. If heavy batteries are the root cause of the mass penalty, why don't we just invent a better, lighter battery?
The holy grail.
Right. Every tech blog has been promising us solid-state batteries for almost a decade. They call it the holy grail of the EV transition.
And the premise of the solid-state battery is brilliant. The goal is to replace the highly flammable liquid electrolytes currently, sloshing around inside the battery with a solid, non-flammable ceramic material.
Okay. And that makes it lighter?
Well, doing this would allow engineers to use pure lithium metal anodes. It promises 400 to 500 watt-hours per kilogram, which is effectively doubling our current energy density.
Wow.
While charging in under 10 minutes and completely eliminating the risk of a battery fire.
That sounds like an absolute miracle. So why aren't they in my driveway right now?
Because they are severely delayed, widely pushed back to the early 2030s. And the reason is a fascinating mix of chemistry and corporate economics.
Okay, lay it on me. Let's start with the chemistry.
Let's look at the chemistry first, highlighted by a landmark 2026 microscopy study from MIT. For years, scientists thought the main barrier to solid state was lithium dendrites.
Wait, what exactly is a dendrite?
Imagine microscopic metallic needles that grow inside the battery during fast charging. Eventually, these little needles grow long enough to pierce through the separator and short-circuit the entire battery. And the working theory was that these dendrites were piercing the solid ceramic through pure mechanical force.
Like a literal needle popping a balloon.
That was the assumption. So engineers just kept trying to make the ceramic physically harder. But the MIT data proved that approach was entirely wrong.
Oh, really?
Yeah, they discovered it's actually chemical degradation. When you subject the battery to the high electrical currents required for fast charging, the lithium ions cause the ceramic to electrochemically corrode. It undergoes microscopic volume contraction and becomes severely embrittled.
Wait, so the electricity itself is chemically rotting the ceramic?
Yes. The MIT researchers noted that the ceramic is, and I quote, tough as a tooth when it's just sitting on a testing bench, but the simple act of passing a high electrical current through it makes it brittle as a lollipop.
Brittle as a lollipop. That is an incredible visual and just a massive engineering headache. But let's play devil's advocate for a second. Let's say a team of brilliant chemists solves that lollipop degradation problem tomorrow. Can automakers just start churning these out?
No, and this brings us to the second major bottleneck, the capital expenditure, or CapEx, standoff.
Oh, it always comes down to money.
It really does. The global battery gigafactories that exist right now, representing hundreds of billions of dollars in investments, are explicitly built for wet slurry processing.
What does wet slurry mean in this context?
So they use highly toxic industrial solvents, specifically one called NMP, to dissolve the battery materials into a liquid paste. They smear this paste onto metal foils, and then they run it through drying ovens that are literally kilometers long.
Kilometers long just to dry it?
Yeah, to evaporate the toxic solvent and leave behind the active material.
That sounds incredibly energy intensive.
It is. Transitioning to true solid-state batteries requires completely ripping out those kilometer-long drying ovens and switching to dry electrode processing, or DEP.
Which is better.
Way better. Dry processing cuts manufacturing energy use by 71%, which is fantastic for the environment and the bottom line.
But I'm guessing the transition to dry processing isn't cheap.
Not at all. To build a new dry electrode plant costs between $2 billion and $5 billion.
Ouch.
And given that consumer EV demand has seen some cooling recently, automakers are acting like rational corporations. They absolutely refuse to bulldoze their brand new multi-billion-dollar wet slurry plants.
So it's like trying to force the entire industry to upgrade their smartphone operating system, but doing so requires them to physically demolish their factories and build new ones from scratch.
Exactly. The industry is essentially settling for semi-solid hybrid batteries as a stopgap measure, just so they can keep using their existing assembly lines.
Right.
So the delay of the solid-state miracle isn't just a science problem. It's a multi-billion-dollar standoff between physics and corporate balance sheets.
Okay, let's step outside the car entirely. Let's pretend the MIT scientists fixed the lollipop problem, and some CEO somewhere writes a $5 billion check for a new factory. Once the magical car rolls off the lot, the driver still has to plug it in.
They do.
And our dossiers point to a severe systemic bottleneck that lies completely outside the vehicle's engineering.
Yeah, we're looking at the electrical grid itself. Specifically, we're in the middle of a global supercycle crisis hitting the supply chain for power transformers.
Okay, I understand that charging millions of cars takes a lot of power, but why are transformers specifically the breaking point here?
Well, to cure consumer range anxiety, we need level 3 fast chargers.
Right, the ones that charge in like 20 minutes.
Exactly. These stations demand immense concentrated localized power. We're talking 500 kilovolt amps to over 2 megavolt amps per station.
Give me a sense of scale for a megavolt amp.
Think of it like trying to hook a high-pressure fire hose directly to a residential drinking fountain.
Oh, wow, okay.
To step down that extreme high-voltage grid power into something the car can actually use without exploding, you need massive, highly specialized power transformers.
Makes sense.
And when you combine the aggressive EV expansion with the integration of wind and solar farms and the explosive power demands of AI data centers, the global demand for large power transformers has surged 116%.
116% spike in demand for heavy infrastructure hardware. I mean, that has to be obliterating the supply chain.
It is paralyzing it. Lead times for large power transformers used to be a very reliable 12 to 18 months. Today is 36 to 48 months.
You're kidding.
And for the highly specialized ultra-high voltage units, developers are facing delivery windows of 120 to 144 weeks.
Wow.
That is over 2.5 years just waiting on a single piece of steel and copper.
Wait, if the demand is that insanely high, why aren't manufacturers just running a third shift or building new plants? Like, it can't just be a lack of money.
It's not. It's a lack of raw physical materials. The crisis is driven by severe shortages of two things. First is copper, which has been trading incredibly high, fluctuating between $8,500 and $10,500 a ton.
Okay, copper is expensive. What's the second thing?
The second, and even more critical, is GOES.
GOES, what is that?
Grain-oriented electrical steel.
Okay.
It is the absolute metallurgical foundation of every modern transformer core. You cannot just use regular steel. GOES requires highly specialized, energy-intensive cold rolling, followed by precision laser scribing.
Laser scribing.
Yeah, that laser scribing process literally alters the magnetic domains of the metal so it can handle extreme voltages without melting from the magnetic friction.
That sounds incredibly niche to manufacture.
It is, and global production is entirely maxed out. And in the United States, it represents an acute national vulnerability.
Why is that?
Because currently a single company, Cleveland-Cliffs, is the only domestic producer of GOES.
Only one.
Yeah. It creates a fragile single point of failure for the entire electrical grid, pushing high-grade GOES prices up to $4,500 to $6,000 per ton.
This highlights such a fascinating clock speed mismatch, you know?
What do you mean?
Like, software engineers can write a brilliant AI grid balancing algorithm in an afternoon. Automakers can stamp out a car chassis in a few days, but you absolutely cannot agile your way through a steel mill.
No, you really can't.
We are trying to run a 21st century software and battery revolution on a mid-20th century heavy metallurgy timeline.
That is the perfect way to frame it. And the EV networks are actually losing the bidding war. Tech giants are currently sitting on an estimated $650 billion in AI infrastructure budgets.
Oh, so they just buy it all up.
Exactly. They're easily outbidding utility companies and charging networks for this finite supply of heavy electrical gear. The EV revolution is functionally tethered to the plodding speed of laser-scribed steel.
So, faced with heavy batteries, billion-dollar factory upgrades, and a totally gridlocked electrical system, it's no wonder legacy automakers and the fossil fuel industry are aggressively pushing an alternative.
Right, they see an opening.
They want a loophole to save the internal combustion engine, and they are pitching something called synthetic e-fuels.
Yeah, and e-fuels are, an incredible feat of chemical engineering. They're designed to be chemically identical to traditional gasoline, meaning you could just drop them into any existing combustion engine.
But without the geopolitical baggage of, drilling for oil.
Correct. You use renewable electricity to split water into green hydrogen. Then you pull carbon dioxide straight out of the atmosphere.
Okay, carbon capture.
Right. You combine the hydrogen and the CO2 using something called the Fischer-Tropsch synthesis process to create liquid hydrocarbon fuel. And because the CO2 released from the car's tailpipe is mathematically equal to the CO2 captured from the air to make the fuel, it is technically net zero carbon.
And that secured a massive legal loophole in the European Union's 2035 combustion engine phase-out, didn't it?
It did. Policymakers basically viewed it as a way to maintain the status quo while still hitting climate targets.
I mean, it sounds perfect on paper. We keep our cars, we keep our gas stations, we avoid the heavy batteries, and it's net zero. What does the data say is the catch?
The catch is a catastrophic mathematical failure known as the efficiency waterfall. We have to go right back to the thermodynamic limits Sadie Carnot taught us at the very beginning. E-fuels suffer compounding energy losses at every single step of their creation.
Walk me through the waterfall. Where are we losing the power?
First, the electrolysis to get the hydrogen plus the carbon capture process immediately lose about 30% of the raw renewable energy input.
Ouch. Okay.
Then, the Fischer-Tropsch synthesis and the physical transport of the liquid fuel lose another 40% of whatever is left.
It's just shrinking and shrinking.
Exactly. Finally, you pour that hyper-engineered fuel into a combustion engine, which, as we established earlier, wastes another 70 to 80% of the energy as pure heat.
Let me get this straight. We are using precious, expensive renewable energy to power giant carbon-sucking vacuums and high-tech chemical reactors just so we can put that incredibly expensive liquid into the exact same engine that drops 3/4 of our pizza on the floor.
Yes. When you multiply all those systemic losses together, the total well-to-wheel efficiency of an e-fuel car is a dismal 10.5 to 20%.
Unbelievable.
Compare that to the battery electric vehicle, which again sits at 59 to 77%. If a nation wanted to replace its current passenger fleet with e-fuels instead of batteries, it would need to generate 3 to 6 times more raw, renewable electricity.
That's a massive difference.
Huge. It would require vast, unmanageable tracts of land dedicated entirely to wind and solar farms just to create the synthetic gas.
So it's just a complete thermodynamic absurdity for a daily commute?
It is entirely unviable for passenger cars. I mean, e-fuels are scientifically brilliant, and they will be absolutely necessary to decarbonize transoceanic aviation and maritime shipping sectors where batteries are just physically too heavy to ever work.
Right, you can't fly a plane on batteries yet.
Exactly. But for lightweight passenger vehicles, the data widely views the e-fuel push as a regulatory delay tactic designed to protect legacy intellectual property and existing factory investments.
So to bring this full circle, the death of the internal combustion engine isn't purely a matter of environmental activism. It is dictated by the cold, unforgiving math of systemic efficiency. But as we've unpacked today, the EV victory isn't exactly clean either.
No, it is a messy transition.
Right.
We haven't eliminated our problems. We've merely shifted the burden of engineering.
Right.
We've traded heat waste for a mass penalty. We've traded tailpipe emissions for tire microplastics. And we've traded a geopolitical reliance on drilled petroleum for a highly fragile supply chain, paralyzed by the scarcity of solid-state ceramics, raw copper, and electrical steel.
You know, we started this deep dive with the mission of looking past the noisy political headlines. Hopefully, you now have a complete physics-based understanding of the greatest industrial transition of our time.
Yeah, hopefully it makes more sense now.
You understand why the combustion engine is failing, why the battery is so heavy, and why the grid is struggling to keep up.
The automotive industry has finally solved the thermodynamics of forward motion, but it is now violently colliding with the infrastructural limits required to actually sustain it.
Which leaves us with one final lingering question to ponder as we wrap up today. As the demand for electricity skyrockets simultaneously from the EV transition and the explosive, relentless growth of artificial intelligence, who ultimately gets to decide which sector gets the electrons first when the grid simply can't supply both?
It's going to be a fierce battle.
Think about that the next time you plug in your devices. Thanks for joining us on Insight. We'll see you on the next deep dive.